We did it in the morning.
Inside the conferences.
Yes?
ABC. Maybe.
Yeah, that's the question. How do you make full scale
Wait.
on a PC?
First you can just
Sure,
move them, and
please.
then I don't know how to move.
View. View mode.
Okay, and then it's just here, right? No?
No.
Here. Sorry.
Let's make sure. Does it work?
Wait.
This.
Okay. Let me try here.
Let me. This is better.
Okay.
It's better. It's.
No. Yes.
It's moving?
It's 2 times.
Okay. Our next speaker is Professor Anabela Cruzeiro from Lisbon, who's going to talk to us about convexity and, stochastic radiation principles on Lie groups. Please.
Thank you very much. Okay, I first would like to thank the organizers for the invitation. It's a real pleasure and an honor to be in this university, especially on the occasion of the celebration of Sergei Fomin, who is, as you know, a reference to every mathematician in the world. And actually every student of mathematics in the world. Don't even have to be a mathematician. You learn at university from the books, and so it's, thank you very much. Okay, so I'll be talking about stochastic radiation. Let me think. So before I forget, this is a joint work with the chairman and also with Xin Shen from Shanghai Jiao Tong University. The general idea that I'm be talking about, well, there are 3 sorts of problems which, well, I mean, this is same kind of problems, but to start with, we want to have we want to have variational principles for dissipative systems. Essentially, that's the main first idea. So that gives the rise to ODEs or PDEs according to the space being finite, the situation being finite dimensional or infinite dimensional, and sort of generalizing what people do in classical geometric mechanics. They derive equations of motions from variational principles for conservative systems. So the idea is that by considering perturbations, stochastic perturbations of the Lagrangian motion, we can get a stochastic variational principle for this dissipative system. So dissipativeness is encoded in this perturbation as it's encoded in the Laplacian fourth Brownian motion. So this is the first idea. So we want to get deterministic ODEs or PDEs. So the first idea is that we get the same deterministic equations with the same action function, same Lagrangian classical one. The only difference is that the Lagrangian picture is stochastic. So we compute this Lagrangian on a stochastic system, generalizing the notion of derivative, using a generalization of notion of derivative, and then you get the classical PDEs or ODEs, again, according where you are in infinite dimensions or finite dimensions. Then one can also generalize this approach to get stochastic PDEs or SDEs, again, depending on the dimensions, by also randomly perturbing the Lagrangian. So this is something on the top of it. You can also derive these stochastic systems if you want to. Then the Lagrangian is not only the classical one, you have to make a perturbation also there. So there are here, in this case, 2 perturbations. probabilistic perturbations. And finally, we may want to consider all these systems with effective quantities depending on the application, so we also generalize this. So I'll be trying to sort of take in consideration that one may be only interested by the first kind of problems, or by the second kind of problems, or even by the third kind of problems. So I'll be using some colors, and then I'll tell you what the colors mean after. But first, let me speak about the general framework. So the general framework, as in classical geometrical mechanics, will be a Lie group, where we consider, well, a left or right. Well, it's the same. I mean, some change signs, but something changes in the signs. But essentially, you can consider left or right translations and left or right invariant metrics, plus a connection. You again, right or left invariant, torsion free. So E will be denoting the identity of the group, and curl G the Lie algebra that we identified with the tangent space at the origin, at the identity element. And then you consider also this TGLG, which is the tangent map. So this is just the derivative of the left translation in the left invariant case, or the right translation in the case of right invariant case. If you are interested by advective quantities in the systems, if not, you can skip this part. But if you are interested also in advective quantities, then you have to add an extra structure to this to the framework, and this will be given by some vector space. U star will denote its dual, and then G has a left or right representation. Now I'm starting with left, okay, but it's the same. The left representation on this vector space. This vector space will, will describe the advective quantities that you want to characterize, to consider. And then there is, this representation, induced representations also on the Lie algebra and U star. And then there is this diamond operation. I'm not sure if it has a name. No, it doesn't.
It's the momentum. For those of you who know symplectic geometry.
Okay, I'm not included in those who know really symplectic geometry. So anyway, so this is this diamond operator that is defined there. It's quite simple to define, and the meaning of it is something else. But it's defined on U times U star with values on the dual of the tangent map by this simple and light came in. Okay, so this is what I will be calling the diamond operation. Okay. So now about the stochastic framework. So we will be considering this Lagrangian trajectory. So G will be describing the position of the system. And it will be, as I said, random. I mean, it will be a stochastic process. Actually, it will be more than that. It will be a diffusion process on values of the Lie group. So G will stand for things which are have values on the group G, and are defined by. So there is some drift U, which for the moment you may think about it. As just a deterministic function, then computed of course on the process, but just a deterministic function for the moment. And HI are some bunch of vector fields. It don't even have to be not orthogonal basis or something like that. It's just a bunch of vector fields. On the Lie algebra, and so this part is the perturbation of the classical part. If you are in classical geometrical mechanics, you wouldn't have this part, you would just have the U. So this, as I said, stands for the perturbation in the Lagrangian picture. So WR, I are independent Brownian motions. Each time I write dy, this is Ito integral. And then if you want to write it in terms of Stratonovich integral, there is this extra correction in terms of the covariant derivative. Okay, so now the generalized derivative, so when we write here d with the nabla, it's exactly this part. So the part that doesn't have the martingale part, so that doesn't have this one. Okay, so why is it called a generalized? This is something very well known in stochastic analysis, by the way. This is nothing really new, this generalized derivative, but just to make sort of intuition for those who are more interested by the geometric mechanics part. Sorry, okay. So why is it called a generalized derivative? So essentially it's the drift, okay? So if you can define it by parallel transfer, so you have something with values on the Lie algebra at a certain, over some g of t, so you can parallel transport it and to the origin, and at the origin this is again the drift of the pullback of the diffusion to the origin, but can be given in terms of this derivative, which also it's very well known in stochastic analysis that it's a sort of derivative, but you have to put here conditional expectation, otherwise it would not be differentiable. And this is known since Ito actually, but it was very much used by Nelson for in a dynamical viewpoint, but anyway. Okay, we can also define the martingale part with so we split the motion, the Lagrangian motion, into two parts. One is the drift, that we call generalized derivative because it's a sort of derivative, and then the other part is the martingale part, given by the Brownian motion. Okay. Now, okay, so I have to spend a little bit of time here because I'm going to see what kind of action, so we are interested in variational principles, what kind of action do we consider. Okay, so first, little l is a standard Lagrangian, right? The g's are like before, so they are diffusions driven by some bunch of vector fields and with the same drift u. So G1 and G2 have to be, so there are distinction because the HI, the vector fields that are in front of the Brownian motion may be different, but the same drift. And then, okay, so the first part of, if you are only interested in looking at what we are doing in order to obtain dissipative systems, but like PDEs or ODEs, but classical ones, you only look at the black part of this formula. So, which is of course much smaller than the rest. So this is good. So only look at the black part. So forget about the colors. If you are only interested in this. If you are also interested in the advective quantities, then you look at the red thing. So the alpha is the evolution of some alpha naught in the dual of this vector space, so it will represent these advective quantities, right? So you can be looking at all this and this. Now, if you are interested in SDEs in infinite dimensions as equations of motion, so not only the deterministic ones, but perturbations of this one, or in infinite dimensional framework as PDEs, then you look at the blue part. So only in this case, so I'm not sure that there will be a lot of people interested in the blue part, so I don't know. Anyway, you can, again, you can look at this in different ways. Just look at the black and red if you are interested in the vector quantities, and then if you are really interested in stochastic PDEs or something like this, you look at the whole thing. So this part of the Lagrangian, the black one, is just the standard Lagrangian, right, the deterministic one, except that it's computed on this generalized derivative instead, of course, of the usual derivative, since it does no sense. By the way, if you have no perturbation on the particles, on the trajectories of the particles, this, of course, is exactly you go back exactly to the framework of standard classical geometric mechanics. Okay, so this part is a perturbation, so this part is given by some function q of this derivative and alpha. So this is absolutely stochastic, right? So you can see this as a stochastic perturbation of the classical action. But in this first line, again, there is only the standard Lagrangian computed on the only difference actually is that the g's are stochastic, and this has to be taken in some regularized sense since you don't have a derivative in time for diffusions. Okay, so by the way, in the case you don't have the blue part, actually you have to put an expectation in front of the alpha so that this is something deterministic. But okay, so this is the action functional. Now the domain of this action function are these G1 and G2, so these are general semi-martingales, but in particular those of the form that I wrote before, with a fixed drift U and some regularization given by some vector fields that I called HI in front of the mound in motion. And what do we mean? I mean, we have we are talking about a variational principle, so we have to derivate, right? So we have to see in what directions you derivate. So these are directions that are given by some V, so some vectors fields depending on time eventually. And then you consider the flows along these vectors in the direction of these vector fields. And then this will be the variations. I mean the set where you want to modify your trajectories. And if you are only interested again in the blue-red part, V can be just deterministic. If you are looking to the blue part too, the blue part being the SPDEs, then you consider V eventually random too. Then you say that G1, G2 is critical for the action function if, of course, for every such variation, the derivative is 0. Here we compose, I wrote the formula with the composition on the right because this is a left invariant case, otherwise it's composed with the left. Okay, so again, these are the DG I's. So the J. The DG is J, so the G1 and 2 stands for different vector fields. U is the same. Now I'm assuming, just for simplicity, that these covariant derivatives of HI are 0, but that's not a fundamental assumption. It's just that it simplifies a bit the formula, and so I'm not talking here about all the generality of what we have done. I'm trying to simplify as much as I can, so this is not a fundamental assumption, but by the way, it is verified by a lot of vector fields, so it's not also an enormous restriction. So the main theorem is the following. So again, this is the old theorem, taking into account all colors, say. And it says that G1, G2 is critical for the action functional in the sense explained before with these variations. If and only if this process, which is the same for all G, so it's the drift of all these G1 and G2, coupled with the alpha T, which is the evolution, remember, of the initial conserved quantity. So these things are in the vector field, dual of the vector field U. If and only if it satisfies the semi-direct if you want the red part, stochastic if you want the blue part, otherwise just red, this equation. So let me spend also some minutes, some little time in looking at the equations of motion. So first let's look just at the black part, so no no advected quantities, no randomness in the equations of motion, right? So this is, think about L having the kinetic energy, then dl du, which is the functional derivative of the Lagrangian, will be just u, but we can have another Lagrangian. So the derivative of u, or generally speaking dl du, is, okay, forget about this, is the operator add star on dl du alpha plus this k. Okay, so if you are not stochastic, if you were in geometrical mechanics, deterministic geometrical mechanics, you will be only having this, right? So this is, I suppose, very much familiar in geometric mechanics. So the only thing which is added for the u, and remember there u is just a deterministic vector field that you put to define the drift, as a drift to define the motion of the g's there, then it will be this. And the only difference now is that we have an operator here that will account for the dissipativeness of the system, and I will explain you what the k is, but okay, you just think that there is an extra operator there. If you want advected quantities, okay, then you will have also the differential of the alpha, and again here is what you would obtain as if this was not stochastic with the diamond operator here, and this is the expressions for the d alpha. Again, there is this dha, and if you think there is no dha, this again will be the classical motion for these advected quantities in classical geometric mechanics. And finally, if you want SPDEs or SDEs, well, for the moment this is finite dimensional nodes, so this is SDEs, then you will have some extra, some perturbation of the motion, and u in this case would be eventually random. Well, it will be random. Okay, so the only thing I think it's left to explain is what the hell is this k. The k is supposed to encode this dissipativeness, so this is the extra thing that you get from going to deterministic particle motion, Lagrangian motions, to stochastic ones. And the k has in fact a very strange form, unfortunately, in the general case. So k is pretty complicated, actually. You don't have much intuition what is k. But fortunately, there is one case which is actually the right invariant case, and when this is zero, which again is not such a drastic assumption, where the k actually is just the Ram-Hodge, or I don't know how you call it, but I call it the Ram-Hodge operator in the Riemannian geometry. So this is the Laplacian on forms, on vectors, and this is the R is the Ricci actually. Okay, so it is a quite strange operator. When I look at it, I don't see anything particular, but it does encode dissipatives. It's a second order operator, and it has a very nice form when you consider the right invariant case. Okay. Yes, the right invariant case is the same thing up to some changes as science, and the proof of all this is essentially, it's long, but it's not difficult in the sense that it's essentially use of Ito calculus only groups. Okay, now about applications, actually. Concerning applications, I could show you some applications in finite dimensions. You get some eventually interesting, or at least funny motions. For example, generalizing the rigid body motion with some extra randomness or things like this. But I would like mainly to concentrate on the what I think are the really interesting examples, which are Navier-Stokes, compressible Navier-Stokes, and things like this. So these are not examples per se of the framework I talked about, because so far I only considered motions in finite dimensions. And now I'm going to use a group which is infinite dimensional. Okay, so things don't go immediately as an application, because first you have to make sure that your underlying Lagrangian trajectories are well defined. Okay, that's not an enormous, I mean, there are results, infinite dimensional existence of infinite dimensional diffusions, there are results. And then in some way, for the proofs, you have to do them step by step again for each case. So it's not that you can just apply and say it's the same thing. Well, it's not quite the same thing, but it does work in many examples if you are careful enough to check each step somehow, or the main steps that make the proof work. So, infinite dimensional case, the group that I'm going to look at is GS, which is well, not necessarily diffeomorphism. You only have to have homeomorphisms of some manifold M of Sobolev order GS, so that they are regular enough. But you don't need more than homeomorphisms, actually. M can be a general manifold, but here I'm going only to talk, for simplicity, to talk about the torus. Okay, so this kind of flat case, it will be more easier to write down. So GS is an open set of the smooth Hilbert-Elmiford, and it's a group under composition, as we know. The Lie algebra can be identified with vector fields on M. It's not precisely a Lie algebra, but again, proofs have to be done step by step. So we only use things that we can use, then this is not one of them. And then d mu is the Riemannian volume of the manifold. Okay, in the flat case, this is just Lebesgue measure, and we consider the L2 metric on this, corresponding to the volume measure of the manifold you're dealing with for some vector fields, which are this kind of vectors develop a tangent space with some regularity, a Sobolev regularity. Okay, and then you can have a general connection defined on the manifold, which I wrote down the expression there. But actually we are on the torus, so it's more simple, and you can also consider the submanifold. Well, submanifold, I should have put a comment. Okay, so it's the part of the group consisting of not only the homomorphisms of the manifold, but those who keep the volume measure invariant. So this is, of course, the case where you want to look at incompressibility flows and Navier-Stokes. Okay, so the corresponding Lie algebra here is the divergence-free vector field, so that the flow is invariant. The connection can, in the case of the torus, you can just write out the flat connection, flat derivation, and then project it on the divergence-free vector fields, and you get a very simple connection to work with in this case. Now we are in the right invariant case, by the way, in this one. Anyway, so we are, as I said, you cannot apply generally the theorems, but you go on, you look at the proof, and things survive, adapting the general idea. So we can get, so this is a sort of a first result, where no advected quantities first, so the red part is out. The blue is absolutely out. So there's only black, right? So there's only the usual Lagrangian, I will only want to consider the usual Lagrangian on random trajectories and see what kind of equations of motion it provides in this infinite dimensional framework. So the G's, the particle the trajectories, Lagrangian trajectories will be, as we are in the torus flat case, this will be just just driven by some vector field u. In this case, in compressible case, divergence-free u. And here the vector fields are extremely simple. I just consider the canonical basis, so this is just Brownian motion. So you have to look at this as a flow of homeomorphisms, according to the regularity of u, of course, as a function of theta. So this gives you a flow of homeomorphisms. Well, you only need Kunitas, you need Kunitas theory of stochastic flows to get that. Okay, so you have these GGs, and what does our theorem, the black part of our theorem, gives you in this case? It gives you the following. Okay, so the action function, the Lagrangian is the kinetic of energy, so also the simplest possible. The action, don't know why I called it G here, but never mind. So the Lagrangian computed on the generalized derivative of G, so which is U, right? And then the theorem gives you with the adaptation so that it's infinite dimensional, but it gives you that G is critical for the action function if and only if the U satisfies, there exists a P and U satisfies the Navier-Stokes equation with this incompressibility case, because I'm looking at manifold of flows which keep the Riemannian volume invariant. Now, another example will be the compressible case. I mean, the Navier-Stokes equation, but with compressibility. So you have to take into account the density, which will be an advective quantity of the system. So now you need the red part. Okay, so it's black and red. So again, this is the same kind of I'm again on the torus for simplicity, the same kind of Lagrangian particles, these diffusions with a very simple diffusion part with U. Now it's not divergence free, now we are only in the big GS group. Not divergence free. U will be U star will be the vector space where the advected quantities will be leaving, but in this case I just want one advected quantity, which is the density, to complete the picture of the compressible Navier-Stokes equation. And so you alpha 0, well actually I wrote this in general because alpha can be a function or a differential form, and then you have to derive the equation for alpha by stochastic calculus independently, because again you cannot use finite dimensional results just directly. So actually I wrote how you can make the evolution of the alpha. If it's a function or it's a form or whatever, you can have an expression for a stochastic expression for this alpha, which, by the way, again, for the proof uses Kunita's theory of stochastic flows. You know that when you have to use Ito formula, but the function where you apply to is also random. So there are some generalizations of Ito formula, which, well, maybe have been done by other people, but essentially we used here Kunita's result. Okay, so in the compressible Navier-Stokes equation, there is only one advective quantity, which is actually a function, that's the density. And we have this result, so we consider this Lagrangian, so now we have to take into account the density, and here is the entropy. So this is very much, so this is the classical action, so this is nothing new here. This is the classical action for compressible Navier-Stokes derived in stochastic mechanics. So this is the same. So alpha is, rho will be standing for the density that you want to make evolve. So now, okay, again, I'm sorry, there should be some red here. Okay, sorry, the rho is red. So, by this time my colors were a little bit faded away. I'm sorry about this. So there is some red here. But the blue again is, you only look at the blue if you are interested in SPDEs, not in classical PDEs equation. Okay, so but this is the action computed for this rho advective quantity. Sorry about the lack of red. And again here there is a we missed the red. I missed the red, I'm sorry. Okay, so the theorem is that the semi-martingale G and G, so you can have two with the different vector fields, same drift, you remember? So the difference here is that you can have a mu1 and mu2 in front of the Brownian motion, different ones. And then is a critical point for the action, which is associated with Lagrangian, standard Lagrangian for compressible Navier-Stokes equation. If it, and only if it is satisfies these, well, SPDE if you want the blue part, and and PDE if you don't want. So essentially you have, okay, I write it in the case mu1 is equal to mu2 because it's simpler. If mu1 is equal to mu2, there is the stochastic motion if you want the SPDE. And then there is, okay, you see the compressible, you see the term, Laplacian term, the nonlinear Eulerian term. Then there is the pressure term, right, which should be, the rho should be red, and the equation for the rho, which is the advective quantity here. And then you have some extra term. Right. Okay. Now I must say that I'm cheating a little bit. No, I'm not cheating. I mean, this result is okay. But the equation I wrote is not exactly the compressible Navier-Stokes equation that you read in the books. There are some terms missing. Okay? So I just didn't want to impose you an action with even more terms than the ones already there. So if you put some extra term in the, well, you have to believe me or read the paper when it comes out, but if you put some extra term even in front of the, in the action, you get the exact compressible Navier-Stokes equation. So this is not exactly the one. There is some term missing, but it's almost there. You can get this from the action function I wrote. And if you want to get the real compressible Navier-Stokes equation, you have to plug in again even another term, and I didn't want to write it too. So okay. So another example. I'm not sure. I'm almost finishing anyway. An almost example. I'm going to be fast here. I have some minutes. Oh.
Yeah.
Because we
run out of 5 minutes because we all.
Oh, okay, so I have plenty of time. I thought I was just finishing now, but I have 5 minutes. Okay, so this is the magneto-hydrodynamical equations that you may know. And again, these are standard, not standard, I mean, these are deterministic classical equations that you can derive in geometric mechanics. They need some extra advective quantities, which are, so there is the density, there is a B, okay, so there are various things here that I wrote down here. So this is the classical Lagrangian. There is the B, which stands for a magnetic fluid, the D, which is a density, and then there is the energy 2. Related to the temperature. Okay, so this is the classical Lagrangian for magneto-hydrodynamics equations. And then here, when we randomize our particles, so this is the same, and then we consider an action which will depend on G1. Well, there are several viscosity constants that here the mu1s, the mu(I) are viscosity constants in front of the Brownian motion. There are several ones that you can consider, one for each, vectored quantity, and the action function is the same, computed on these g's, which have the expression as before, with the same velocity drift u. Okay, and then you have this kind of equations which generalize the u, so it's the same sort of principle than the one for incompressible Navier-Stokes. And again, I'm cheating a little bit because if you see the books and you look at what is the MHD equation, it has some different terms that we can actually obtain if I modify a little bit the action function to start with, but I didn't want to do that. So, what about, just one final word, what about the existence of critical paths for these actions? Can we deal with this question? Well, there are three approaches that I'm trying to develop with more or less success depending also on the model, because finite dimension models, well, there's not much trouble, things tend to exist there, but not in infinite dimensions. It's much more complicated, and it depends on the specific model you're dealing with. But anyway, the kind of methods that I'm trying to develop here with different co-authors that I didn't mention. So one is entropy minimization results. So when your Lagrangian is the kinetic energy, you can write this action principle, stochastic action principle, as a minimal entropy problem. So again, when it's infinite dimensional, there are some technical problems, but the idea is that you can look at it with the tools of entropic problems, interpolation, and so on. The other one is that you have in these stochastic systems, you have an equation for G, which is which is the one for the trajectory, and you can also derive an equation for U, which is the equation of motion that you get from the variational principle. If you put them together, so dg and du of g, right, you can get, it's like a second order system. You can split it into two parts, or you can see it as a system, and you can go into the theory of forward-backward SEs. So this is another approach to try to solve, to get existence from this equation. Again, depends on the model, because in infinite dimensional spaces, for example, which I think are the more interesting cases, forward-backward SDEs is not so much developed, so you have to see it case by case, and it depends on the functional on the estimates you have on the functional spaces behind. And then you can also, if you don't know that they exist, you can also try to think about generalized solutions in the sense of Renier. Instead of looking for paths, you look for measures. It's a kind of weaker solution, which hopefully gives some fruits too. And so, okay. So these two references here. Thank you for your attention. Спасибо.
Questions, comments? Okay, thank you very much.
Okay. Oh, there was a question.
Oh, there was. I didn't see you. In the meantime,
I can see you.
I think, did you talk about kind of direct methods?
Подождите, пожалуйста.
I mean, direct methods of solving your problems. When you
Before the first we tried, of course. But
Вот прям после этого.
it's not so easy.
Berlin to stochastic optimization.
Yeah, because yeah, we can see as a starting control problem.
Yes.
So yes, but as long
You
as
don't
we are.
enumerate this in your last slide.
Yeah, I did actually. I should. Thank you. No, but as long as you're in finite dimensions, it works very okay. But for infinite dimensions, but it's true. I should have put an extra line to catch
Сейчас радио, а второй как называется? Сейчас я проверю, что
Also another viewpoint.
А, БГ. А вот, все. Теперь мы открываем. Да, это вот view.